Hey everyone, and welcome to The Explainer. Today we're building complete, ground-up conceptual mastery of your Class 10 Science Chapter 3. We are looking at the absolute building blocks of our universe, metals and nonmetals. I am so incredibly excited to guide you through this because by the end of our time together, you won't just be memorizing facts. You'll actually understand how the materials around you behave and exactly why they do it. So let's dive right in.
I want you to literally look around you right now. The screen you're watching this on, the chair you're sitting on, heck, even the oxygen you're breathing in, everything falls into these broad categories. But how do scientists actually tell them apart? Now, you might remember from earlier classes that there are way fewer nonmetals compared to metals. But at a core conceptual level, what truly makes a metal, well, a metal?
Here's our roadmap for today's chapter. We'll be hitting 1. The surface level, 2. The rule breakers, 3. The stress test, 4. The leaderboard, 5. The ultimate partnership, and finally, number 6, check your mastery. Let's kick things off with Section 1, the surface level, focusing on the physical properties of elements.
Let's start with the obvious stuff, right? How elements actually look and feel. If you go through the first few activities in your textbook, taking samples of iron, copper, or aluminium, a really clear pattern emerges. Pure metals have this brilliant, shining surface. We call this metallic luster. They're malleable, meaning you can beat them into thin sheets without breaking them, and ductile, meaning you can draw them out into super thin wires. Plus, if you hook them up to a simple circuit, the bulb glows brightly because they are fantastic conductors of heat and electricity. Nonmetals, on the other hand, like carbon or sulfur, are totally different. They're generally dull, brittle, and really poor conductors. Simple enough so far, right?
Moving on to Section 2, the rule breakers, dealing with exceptions to the rules.
Okay, now here's where it gets really interesting. Nature absolutely loves breaking its own rules. We can't group elements just by their physical properties, because you have to look at these massive exceptions. I mean, we just said metals are solid and hard with high melting points, right? Well, gallium and cesium have such low melting points, they will literally melt in the palm of your hand. And mercury? It's a metal, but it's a liquid at room temperature. Now look at the nonmetals. Iodine has a shiny, lustrous surface. And carbon? It exists in different physical forms called allotropes. Diamond, which is a carbon allotrope, is the hardest natural substance known to us. Meanwhile, graphite, another carbon allotrope, conducts electricity beautifully. So as you can see, physical appearances can be super deceiving. That brings us to Section 3, the stress test. Let's look at the chemical properties of metals.
Because physical properties aren't quite enough to tell the whole story, we need to take our metals into a virtual lab and basically torture test them. Let's walk through how they react with oxygen. If we hold a metal sample with tongs and burn it over a flame, we see that almost all metals combine with oxygen. The core equation you need to master here is metal plus oxygen gives metal oxide. And mostly, these oxides are basic in nature. For instance, if you heat copper in the air, it gets coated with this thick, black-colored layer of copper-2 oxide.
But here is a crucial point for your conceptual mastery. They do absolutely not react at the same rate. While copper just gets a little black coating, metals like potassium and sodium are completely wild. They react so vigorously with oxygen that they will literally catch fire if you just leave them out in the open. Because they're such a massive danger, they actually have to be kept immersed in kerosene oil just to protect them and prevent accidental fires.
Now here is a very special term you must lock into your memory. We said metal oxides are usually basic, but some, specifically aluminum oxide and zinc oxide, act like dual agents in the chemistry world. They show both acidic and basic behaviors. They can react with acids and bases to produce salt and water. We call these rule-bending oxides amphoteric oxides. Make sure you remember that one.
Next, we stress test them with water. And again, we see a massive difference in aggression levels. Potassium and sodium, they react violently with just plain cold water. Magnesium, on the other hand, refuses to react with cold water. It demands hot water to get moving. And then you have stubborn metals like aluminum, iron, and zinc. They won't react with cold or hot water at all. They require superheated steam to finally break down and form metal oxides and hydrogen gas.
This perfectly sets up our final stress test, the displacement reaction. If you put an iron nail into a blue solution of copper sulfate and wait about 20 minutes, a visible reaction happens. Why? Because a stronger, more reactive metal will always bully a weaker metal right out of its solution. Iron displaces the copper. The core rule here is
Metal A plus the salt solution of B gives the salt solution of A plus metal B. This test gives us perfect, undeniable evidence of which metal is truly the strongest.
Which leads us perfectly into Section 4, the leaderboard. Let's talk about the reactivity series.
All these stress tests, burning them, throwing them in water, pitting them against each other, they give us the ultimate data to rank our metals in a descending tier list. This is the reactivity series. At the very top, we have our highly reactive champions, potassium and sodium. In the middle, you'll find our moderately reactive metals like zinc and iron. And look down at the very bottom, silver and gold. This explains perfectly why expensive gold jewelry never tarnishes or corrodes, right? It is safely sitting at the absolute bottom of the leaderboard.
Now for Section 5, the ultimate partnership. It's time to form some ionic bonds. So we know how metals behave on their own, but what happens when a metal finally meets a nonmetal? Let's explore this ultimate partnership using sodium and chlorine. Think of this as the perfect give-and-take friendship. Sodium's electronic configuration is 2-8-1. It has one extra electron in its outermost shell, and it desperately wants to lose it to become stable. Chlorine, on the other hand, is 2-8-7. It desperately needs just one single electron to complete its octet. So sodium gladly gives its electron to chlorine. Sodium becomes a positively charged cation, chlorine becomes a negatively charged chloride anion. Because they are now oppositely charged, they attract each other with incredibly strong electrostatic forces, locking together to form sodium chloride, which is just your everyday table salt.
This exact mechanism, the complete transfer of electrons from a metal to a nonmetal, creates what we call ionic compounds, or electrovalent compounds. Magnesium chloride is formed in exactly the same way, just with magnesium transferring 2 electrons to 2 different chlorine atoms.
Now let's look at the properties of these incredible ionic compounds. Physically, they are solid and hard, but surprisingly brittle under pressure. They'll shatter into pieces. But here is the most fascinating part, and honestly a classic exam favorite: electrical conduction. Ionic compounds do not conduct electricity in their solid state, simply because their rigid structure prevents the ions from moving around. But if you melt them down into a molten state, the heat overcomes those forces. The ions finally have room to move freely, and suddenly they conduct electricity perfectly.
And just to prove how strong that electrostatic grip is, check out their melting and boiling points. The sheer amount of heat energy required to melt these compounds is staggering. Like calcium oxide melting at 2850 Kelvin? That proves how incredibly strong those interionic attractions really are. You need massive, massive energy to break them apart.
All right, Section 6, check your mastery. Consider this your final exam for today.
We have covered immense ground today. Let's wrap up this explainer by applying your new conceptual mastery directly to a classic textbook exercise. Which of these pairs gives a displacement reaction? Think back to our reactivity series leaderboard. To displace a metal, the solid metal you add must be higher up on the leaderboard. So, is copper stronger than sodium? Nope. Is aluminum stronger than magnesium? No again. But what about copper and silver? Copper is above silver on the reactivity series, so copper will absolutely displace silver from a silver nitrate solution. Take a moment to really let that logic sink in. Why do elements react the way they do? It's all beautifully connected. Keep asking these questions, keep testing the rules, and keep exploring the fascinating world of science.